Hello, I am B.G. Fernandez. I am with the Department of Electrical Engineering, IIT Bombay. For another 40 lectures also, I will be dealing with various aspects of power electronics. Now, what is the definition of power electronics and what is the goal of power electronics? I will tell you sometime later. Okay. Power electronics is one of the basic courses in electrical engineering. It is a very interesting course, an important course, and relatively easier to understand. So, all three in one course. Okay, very interesting, very important, and relatively easy to understand. Okay, so it's a very basic course in electrical engineering. So it can be termed as a course on circuits. I will be using Kirchhoff's voltage law, that is KVL, Kirchhoff's current law, that is KCL, and behavior of inductor and capacitor for DC excitation and AC excitation. Okay. So these are the prerequisites. Definitely all these topics you would have studied in your 11th or 12th standard. Okay. Having said that power electronics is a basic course, to appreciate this course, you need to know, or you need to have a reasonably good knowledge on circuit theory, good knowledge on electrical machines, power systems, power semiconductor devices, little bit of device physics. So if there are devices, definitely you need to know little bit of analog electronics, digital electronics, control theory, and microprocessor or microcontrollers. So in this sense, so power electronics is a multidisciplinary course. So little bit of almost all the branches, all the subjects in electrical engineering is being covered, or you need to know the topics to appreciate this course. Okay. So I will not talk much on this course. I expect you to explore more about it, okay, during the course. So the outline of the course I have divided into 6 parts. Okay. One is introduction. Okay. Second is power semiconductor devices. Power semiconductor devices, they are termed as the heart of power electronics. I will repeat. So power semiconductors can be termed as heart of power electronics. Is that important? Okay. Then various circuits in power electronics, they can be classified into broadly 4 areas. One is input is AC, output is DC. Okay. Second one is input is also DC, output is also DC. Okay. So DC to DC converters. Third, input is DC, output is AC. DC to AC converters. Okay. And last one, see we have here DC to DC. So there will be AC to AC converters also. Input is also AC, output is also AC. Okay. So we will study these various converters in detail. Simultaneously, we will study where exactly these converters are being used in real time or real life situation. Okay. So the various books that I am referring, they are these. Okay. I have just given them in alphabetical order. Okay. First one is M.H. Rashid. Title is Power Electronics, Circuits, Devices and Application. Okay. So it is by Prentice Hall of India. It's published by Prentice Hall of India. Third edition is the latest one. It is published in 2004. Third edition in 2004. Okay. Second one is Ned Mohan. There are three authors. One of them is Ned Mohan. Title is Power Electronics, Applications and Design. Published by John Wiley and Sons. Okay. Third edition in 2002. Okay. Third book, Cyril Landa. Title is Power Electronics. Published by McGraw-Hill Company. Again, third edition. Year of publication is 1993. Okay. And the fourth one, B.K. Bose. Title of the book is Modern Power Electronics and AC Drives. Okay. Pearson Education 2002. Okay. So these are the four books that I have referred. Other than that, I have referred the papers which are published in international journals. Okay. Apart from these four books, there are other books also. There are a lot of books are available on power electronics. Okay. Now, before telling you about or giving you the definition of power electronics, I'll just show you or just tell you the quotes that appeared in international reputed journals of power electronics. Okay. There are basically 4 IEEE journals. Okay. One is IEEE Journal on Power Electronics. Second is IEEE Journal on Industrial Applications. Third is IEEE Journal on Industrial Electronics. First one is Power Electronics. Second is Industrial Application. Third is Industrial Electronics. Fourth is Power Delivery. Okay. So I am just showing you some of the codes that are published or appeared in these journals. So I just want to tell you, to publish a paper in these journals, there is a rigorous review. Okay. So after reviewing, paper gets accepted and it is being published in those journals. And I am just showing you some of the quotes that appeared in those journals. See, one of them is, we now live in truly global society. Okay. In the highly automated industrial front, with economic competitiveness of nations, in future, two technologies will dominate. What are they? One is computers, and second one is power electronics. The former, that means computers, providing intelligence as to what to do, and the latter, that the power electronics tells us the means to do it. Okay. Computers, they provide the intelligence, and this is power electronics means to do it. Okay. So power electronics is being compared with computers. These are the two technologies that will dominate. Okay. And all of us know computers has become some sort of a household item, very important, being used everywhere. And over the years we know how, over the years we have seen how popular they have become and how it has affected our lives. Okay. At the end of the course, you will realize that the power electronics is also has become, or power electronics equipments, they have become some sort of a household items and is being used everywhere. So that is the reason I told you that power electronics is a very important course, very important, and is very interesting. Okay. And second quote I would like to give you: modern computers, communication and electronic systems get their lifeblood from power electronics. See the comparison. They get their lifeblood from power electronics. Okay. And third quote, again in IEEE paper: solid state electronics brought in the first electronics revolution, okay, whereas solid state power electronics brought in the second electronic revolution. The various milestones in power electronics I will tell you sometime later. Okay. Now let me tell you the energy scenario. Globally, 87% of total energy, 87% of total energy comes from burning the fossil fuel. Okay. Fossil fuel is coal, oil and natural gas. 87% comes from burning the fossil fuel. Approximately 6% comes from nuclear. Okay. So they adds up to 93%, and remaining from renewables. Okay. Renewables means wind, solar, hydro. Okay. In our country, it comes around 70% comes from coal. We have major thermal plants. Okay. Majority 70% comes from thermal power plants. Okay. So all of us know there is a limited fuel globally. Okay. See, it has been projected that natural uranium fuel is expected to last for 50 years or so. See, these figures I got it from the literature. Okay. IEEE journals. Okay. So natural uranium is expected to last for 50 years. Oil is for approximately 100 years. Natural gas for 150 years and coal for 200 years. See, this is the projection which is being reported as of now. Okay. So the question that is being asked is that, will the wheels of civilization come to a halt at the end of 22nd century? Because coal is expected to last for 200 years or so. So will the wheels of civilization will come to a halt at the end of 22nd century? I have no answer. And let me tell you one thing, neither me nor you, the listeners, will be around to see the light of the day whether these figures are true or false. But then we owe one responsibility. We need to make a better place to live in for the generations to come. We are answerable for the generations to come. Okay. So we are bound to extend this period. Okay. How do we do this? One is use it very efficiently. Okay. Use the electric energy very efficiently. Second is improve the conversion efficiency. Okay. Use the electric energy very efficiently, or if there is a power conversion from one form to another form, say AC to DC I want to convert, improve the efficiency of the converting equipment. Third is see whether the energy can be produced using renewables. Improve the percentage. Okay. So, three things we can do. I'll just show you a cycle that is used in power conversion. Okay. See, steam is the input, a turbine is driving a generator. Okay. The total loss here itself is of the order of 65%. 65%. Major losses at the steam and turbine end. Again, this figure I got it from IEEE journal. Power is being produced. There is again, this is the various power transmission levels. So generator is located at a remote end, consumed at the bulk of the consumption takes place in the urban areas. Okay. So this is the power transmission, and maybe here is being utilized. Okay. And these are the various percentage losses. There could be minor changes, that's okay. If you find here only 16.7% power that is left here. Okay. 65% losses here, and finally it arrives here with just 16.7% that is power that is left. Okay. So if the input is 100 kilowatt of fuel energy, if 100 kilowatt is the input to the input, output is around just 15 to 20 kilowatts of useful work. I'll repeat, 100 kilowatt is the input of a fuel energy. How much do I get? Output is of the order of 15 to 20%. So the question is, why spend much effort on motors and their equipment when the losses are at the front end? Why to worry about conversion, if improve the conversion efficiency of the equipment or the machine, when the bulk of the loss at the front end or at the turbine end itself? See, answer is very simple. Every kilowatt of loss saved at the process end, see here, every kilowatt of power that is saved here, every kilowatt that is saved here results in saving of 6 kilowatts of fuel energy here. 6 kilowatts. Okay. 1 kilowatt of is here is equivalent to 6 kilowatt here. Okay. So that's the reason I told you that improve the efficiency, conversion efficiency. Second is use the electrical energy efficiently, and if possible try to explore more on renewables. Now, what are the problems that are associated with the nuclear or thermal power plants or burning of fossil fuel? What is the problem? Nuclear power plant, waste handling is still a problem. Waste handling is still a problem. Safety of nuclear plants. What about burning of fossil fuel? They give out to carbon dioxide, ozone, carbon monoxide, nitrogen dioxide, NO2. Coal burning would give out to fly ash. Global warming, temperature goes on increasing, global warming. Other day I read in one of the national dailies, it says that every year Mount Everest is losing its height at the rate of 10 centimeter. This was reported in the other day in one of the national dailies. Every year Mount Everest height decreases by 10 centimeter. That's because of global warming. That has resulted in climatic changes. It affects agriculture and vegetation. Okay. So in 1997 there was a conference at Kyoto, Japan. The developed countries, what they decided was to cut down on the emission of gases by specific targets. In other words, try to reduce the burning of fossil fuel, try to reduce the urban pollution. Now, major constraint in urban pollution is again IC engine vehicles. Okay. Can you do something about reducing the urban pollution? Okay. So looks like there is a way out, looks like there is a solution to all these problems. Okay. We all know bulk of the power that is being consumed by electric motors, bulk of the power is being consumed by electric motors. And what are the majority of the loads? Major loads are induction motor driving either a fan type of load or a pump type of load, fan, pump, compressors. Bulk of the power that is being consumed globally is induction machines driving either a fan type of load, pump or compressor type of loads. And we know that induction motor, the speed is approximately constant. For all practical purposes, all the machines that we have, DC, separately excited DC machine, induction machine, almost constant speed. Speed doesn't change much. Okay. And another bulk power consumption is by lighting. Lighting consumes another good percentage of power that is being produced globally. So if you try to save on this power on lighting as well as power that is being consumed by motors, if you try to reduce, okay, there is going to be a significant reduction in the overall saving of electrical power. So if I try to save 1 kilowatt of power at the load end, 6 kilowatt of approximately fuel can be saved at the input. Okay. I said bulk of the power is being consumed by induction motors and that are driving either fan, pump or compressor. What sort of a torque speed characteristics of these loads? TL, the load torque, is proportional to square of the speed. TL is proportional to square of the speed. So look here, see here. So fan type of TL is proportional to omega square. So therefore power is proportional to omega cube. Okay. Now if you want to reduce the discharge through the pump or you want to reduce the air delivered by the fans. Now I am not talking about the 60 watt fans, I am talking about high kilowatt fans that are used in the industry. If you want to reduce the air discharge, what will you do? Either you use a dampers, in other words damper provide a resistance to the flow of air, or use a throttling valve for the pump to reduce the discharge. So by using the dampers in the case of fans, or you using a throttling valve for the pumps, you may be able to reduce, or sorry, you will be able to reduce the air supplied or the output of the pump discharge. The purpose is served. In the sense you can reduce the pump discharge by throttling the valve, by providing the dampers, outlet dampers, you can regulate the airflow. At what cost? Power input remains approximately constant. The drive, the motor taking approximately the same input, whether you have closed the throttle valve to a 30% or 50% or fully open, approximately the same. You are able to regulate the output. Instead, if you try to reduce the speed itself, speed of the rotation, you are able to regulate the air in the case of fan, or you are able to regulate the discharge in the case of pump. Then what happens to the input then? See here, power input, suppose the ratio of the two speeds is 0.5, omega 1 to omega 2. The ratio is 1/8. See, there is a significant reduction in the power that is being consumed if you reduce the speed of rotation. 1/8, a significant reduction. So you are trying to achieve both, save energy as well as regulate the output discharge depending upon the process requirement. But then again, at what cost? Nothing comes for free. I told you induction machine, or much for that matter all the machines, or for that separately accelerated DC machine, induction machine, or constant speed motors, approximately constant speed motor. Here is a process. I want to change the regulate the vary the output discharge. So in order to save the energy, I want to vary the speed of the rotation. Definitely, in the case of induction machine, we have to change the frequency of the input voltage, because induction motor runs approximately at the synchronous speed. So if I want to reduce the speed of the rotor, I have to reduce the synchronous speed itself. Okay. So I require a frequency converter, because voltage that is being supplied by the utilities is constant voltage, assumed to be constant voltage, and frequency remains approximately constant. Variation is very small. So constant voltage, constant frequency source that is available. Okay. But then I need to change the frequency as of now, because I want to change the speed of rotation. Now what relationship that voltage and frequency will have, or we will see sometime later. So as of now, we require a frequency converter to vary the speed of the induction machine. So using the frequency converter, I told you that we are able to save on electric energy. What are the other advantages? What happens to the induction machine if I directly switch on to the supply voltage and supply rated frequency? Say 415 volt 50 hertz induction machine. What happens if I directly start it, or DOL starting? It draws a large current, could be of the order of 6 times the rated. Okay. Now that current has to come from a source, okay, and flows through the cable to the machine. So there will be a voltage dip. That's why, in a sense, whenever you put on a large HP motor, momentarily the intensity of the bulb comes down. There is a voltage dip. Okay. Second is, a large current should flow through the cable. Okay. 6 times the rated current it can flow. So a stress on the cable is also more if I directly start it. That current is flowing through the machine winding. Okay. Stress on the machine winding also increases. In other words, life of the machine comes down if I directly start it. Now what happens if I try to reduce the frequency itself? If the input frequency decreases, okay, ns minus nr, ns is the synchronous speed, 120 f by p, minus nr, nr is the speed of the rotor. So ns minus nr is nothing but sns, s is slip, स्लाइड में है ना, and at starting slip is equal to 1. So ns minus nr is equal to ns itself during starting. Now if I reduce the frequency, ns has come down. I told you, as of now I am just talking about reducing the frequency. While reducing the frequency, I have to reduce the voltage also. Reasons sometime later I will tell you. Okay. As of now, I just set a frequency converter. It has to vary the frequency of the output. So what is the relationship what is the relationship between the frequency and the output voltage? We will see sometime later. Okay. So if I am trying to reduce, if the output frequency can be reduced, ns comes down. Okay. It so happens that as I reduce the frequency, I have to reduce the applied voltage also. So magnitude of inrush current comes down. Okay. So if the magnitude of the inrush current comes down, the voltage dip gets eliminated, stress on the cable reduces, it improves the life of the machine. Okay. So looks like there are a lot of benefits. One is I am able to save the power. Second is voltage dip gets eliminated, stress on the cable gets eliminated, reduces rather, life of the machine improves. So what next? What happens if the machine is being fed by a constant voltage and frequency supply? Say 450 hertz is running stably, delivering some load torque. Input voltage is 415, rated voltage that is being applied. So V is constant. If V is constant, flux in the machine is constant, and it is the rated flux because I am applying the rated voltage at rated frequency. So air gap flux is the rated flux. Therefore, the constant losses also remain constant. The core losses remain constant. Okay, because flux is constant. Assume that load on the motor is varying. In other words, motor is supplying a variable torque load. If the load on the machine is varying, that is the process requirement, assume that it is changing. The variable losses, which are function of load, they also keep changing. You have kept the input voltage constant, therefore air gap flux remains constant, core losses remain constant. Load is varying, so variable losses also vary. Now what is the condition for maximum efficiency? Condition for maximum efficiency is constant losses should be equal to variable losses. As of now I am neglecting the frictional and windage. So if I am feeding a motor directly from utility supply, wherein input voltage is assumed to remain constant, and if the load on the motor is of variable type, when the machine is lightly loaded, efficiency of the motor is very poor. Okay. So it is possible to improve the efficiency of the motor when it is lightly loaded by decreasing the flux. See, condition for maximum efficiency is variable loss should be equal to constant losses. Now load on the motor is varying, motor is lightly loaded, variable losses have come down, constant losses have remained same, or core losses have remained same. Now I want to reduce the core losses. I can reduce the core losses by reducing the air gap flux density. That I can do by reducing the input voltage to the motor. How do I vary the input voltage to the motor? In the lab, maybe there is an auto transformer. The size of the auto transformer could be as big as the size of the machine itself. So definitely it is bulky, entire overall setup, motor as well as an auto transformer, plus it is expensive. By the way, how are we varying the speed of this fan? We are using a regulator to regulate the speed of the fan. What exactly are we doing? We are applying the reduced voltage to the motor in order to reduce the speed. See, here are two regulators. This is the old one, very rugged. Variation is in steps. Okay? Variation is in steps. If I keep it in very low speed, after some time this regulator becomes very hot, extremely hot. That's the reason we have to mount it on the switchboard, and there are a lot of openings here for the air to flow, so that to cool the entire setup, because there are resistors inside. To cool this regulator, so these are the openings, and becomes very hot when the speed of the motor is very low. In other words, when you introduce the resistance in the circuit, it becomes hot. Okay. Very rugged, maybe. See, here is another regulator. You might have seen a small, elegant regulator. I can have a very smooth control, very smoothly varying speed. Here, just see, steps. This is a contactor type. Here, very smooth. Both of them doing the same function, regulate the speed of the fan. It is mounted inside the switchboard. You can see just the knob, smooth control. So if it is so small, mounted inside the switchboard, definitely heat dissipation is negligible. If there is a heat dissipation, if it gets hot, definitely you have to mount it outside. Okay. So heat dissipation is very low. Very elegant, very elegant. How is this possible? From such a massive regulator, heavy regulator, to such a small, elegant regulator. Maybe this question I'll answer sometime later. See, here is the internal structure of the regulator. Maybe a coil, capacitor, coil, capacitor. Here is a power semiconductor device. I told you supposedly the heart of the power electronic equipment. This is one type of a power electronic device. This power semiconductor device. Power semiconductor device. This is the one. L, C, and small resistors, high voltage resistors. Okay. This is a power semiconductor device. L and C. Okay. So this is being used in our home. Oops. Okay. Very elegant, lightweight. Okay. Very small. No heat dissipation. Conversion efficiencies should be very high because there is no heat dissipation. Heavy. Okay. Step variation in speed. Dissipates power. So definitely power consumption is high. Overall conversion efficiency is low. Okay. So this is another example. Okay. So coming back to the theory, so if I can try to reduce the input voltage to the motor, which is driving a load, a variable load, it is possible to improve the efficiency of the machine. Okay. So you can have neta is equal to neta max, or maximum efficiency even at lightly loaded conditions. Okay. How to do this? We will address this problem. What is the third benefit? See, I was told that in Japan, 70% of the air conditioners, okay, the speed itself is varying, speed of the motor itself is varying. In other words, frequency is being changed. In 70% of the air conditioners used in Japan, they use variable speed drives, whereas this sort of a thing is just not heard maybe in the US. Why? Maybe energy cost per unit may be very low in the US. Japan, it must be very expensive. Looks like everything is being driven by economics. Okay. What is the use of using a variable speed drive in air conditioners? Or to understand that, what happens in the window air conditioners that are being directly switched on or off? There is a thermostat inside. Temperature is being controlled within a band, hysteresis band. When the temperature falls to below a certain value, AC is put off, temperature starts increasing, and when it crosses a upper limit, AC is again switched on. What is the problem here? Same problems, direct online starting of induction machine, voltage dip, voltage cable wire or stress on the cable, and machine life comes down. Instead, can you vary the speed itself, slowly accelerate it, so you can control the temperature very smoothly. Very smooth control of temperature is possible. Air conditioners as well as refrigerators. Okay. What next? Slip ring induction machine. When do we go in for a slip ring induction machine? when the power rating is high. For low power motors, it's invariably squirrel cage is the construction, cage rotor. As the power rating increases, maybe slip ring induction motors can be used. So in any induction machine, S times the air gap power input, S times the air gap power input is dissipated as heat in the rotor. So air gap power input is approximately equal to input power itself. Okay. So S times the input power is dissipated as heat. Now instead of dissipating as heat, can this power be fed back to the source? Okay. Yes. Can I recover whatever the power that is there in the, or the power that is being dissipated as heat, can it be fed back to the source? Or is it possible to increase the starting torque? Possible to increase the starting torque and decrease the starting current electronically? Yes, our machine teacher has told connect a resistor to the slip rings, thereby reducing the starting current and increase the starting torque. Okay. Now can you do this electronically? Okay. See, I am posing various problems to you, and at the end we will see whether these problems can be addressed using power electronics. Okay. More on this we will see in the next class. Thank you.